Right, right. But the bottom line, though, is if you are in the exterior region of a black hole, and let's imagine that you're in an environment where, it is the vacuum, that, no temperature outside of the black hole, just to make things really simple, then you really would be able to detect this radiation that
Yeah, that's
is.
correct, and that's the amazing thing about Hawking's paper. And I mean, I should say, by the way, this paper is really like one of my all-time favorite papers. It's like a Beethoven symphony or something. That paper, so many new ideas. People sometimes say, who maybe don't know, they think, oh, maybe Hawking wasn't that great. Maybe he got a little bit of extra credit because of his the other issues that he had to deal with. But no, you read that paper, and it's just, if
Yeah.
I could write one paper that was a tenth as good as that paper, I would be satisfied.
Yeah. No, it is absolutely amazing. And the
Yeah,
implication that, black holes are not black, that radiation
yeah,
quantum mechanically can escape by itself is an amazing idea, but it does raise a real issue, which is you
that's
began by
right.
noting, that when stuff classically falls into a black hole, you would lose all the information content about its identity, like you said, whether it's a diary, whether it's, gravitons, neutrinos. You would
Yeah.
wonder maybe when the black hole is slowly radiating, all that information would reappear. But I guess
Right.
Hawking suggested strongly that it wouldn't.
Right. And so I think the key point in Hawking's argument is that, so he showed that because of these vacuum fluctuations, this basic uncertainty in what the fields are doing right near the horizon, there's an energy flux going away from the black hole, which is measurable far away, at infinity. You can't really be at infinity, but far away from the black hole. And since energy is being carried away from the black hole has to be decreasing in size, because for a black hole, it's the amount of energy that it has is just the same as its mass, equals mc squared. And so because of Hawking radiation, because of this small quantum flux of energy away from the black hole will gradually evaporate and disappear. And then the fundamental problem is that the origin of the Hawking radiation that we just discussed, which is just this basic vacuum fluctuations coming from combining quantum mechanics and special relativity, is a local effect. It just has to do with what the fields are doing right near the horizon. And it doesn't have anything to do with the stuff that you threw in much earlier to make the black hole. Whether you collapsed a type O star, a type B star, or a neutron star, or whatever you did to make the black hole, all that is much further inside, back at the beginning of when the black hole was formed. And and I think it's good to kind of emphasize the timescales here, right? So when you say you form an astrophysical black hole, by a supernova followed by gravitational collapse. I mean, this is a process which is almost instantaneous, from the point of view of human timescales. And then the supernova blows up and glows for a few months and so on, and then it's over. And the black hole, kind of there's a nebula or whatever that comes out from all the chaos of the collapse. But in the end, there's just a black hole that's left sitting there. And then the Hawking radiation is sort of gradually starts coming out. And if you sit around and wait, you ask how long does it take? Well, I don't want to get in trouble trying to do the calculation exactly in my head in real time, but it's of order 10 to the 80 years. For roughly maybe plus or minus
solar mass about 10 to the 68, but
yeah, so kind of plus or minus 10 in the exponent, depending on what you
good
assume
enough.
exactly about
Yeah.
the size of the black hole. So it's much longer than the time of the collapse, and all the information about